Mars colonization plan is selling you a fantasy. We lack solutions to problems that could cripple or kill colonists within months. Problems that technology alone cannot solve. The real question isn't when we'll colonize Mars. It's whether human bodies can survive there at all. And here is a question. If you landed on Mars and could send one message back to Earth, what would you tell them? I will pin the most creative answer. Let me know in the comments. Now let's begin. When you're standing on Earth, you're protected by two incredible shields that took billions of years to develop. First, there's our planet's magnetic field, an invisible bubble generated by the swirling liquid iron in Earth's core. This magnetosphere deflects most of the charged particles coming from the sun and deep space, sending them harmlessly around our planet. Second, there's our thick atmosphere, equivalent to being underwater by about 10 meters in terms of radiation protection. Together, these shields reduce your radiation exposure to tiny amounts, about 3 millisieverts per year on average. Mars has neither of these protections. The Martian magnetic field died billions of years ago when its core cooled and solidified. Without that protective bubble, the planet sits exposed to the full fury of space radiation. Its atmosphere, though present, is only about 1% the density of Earth's, so thin that it provides minimal shielding. Standing on the Martian surface, you'd receive radiation doses about 100 times higher than on Earth's surface. But here's where it gets truly concerning. The journey to Mars exposes you to even higher radiation levels because you're traveling through deep space, completely outside any planetary protection. Recent data from the Artemis 1 mission in November 2022, which sent an uncrewed spacecraft around the Moon, gave us precise measurements of radiation exposure in deep space. The absorbed dose rate was 2 to 3 times higher than what astronauts experience on the International Space Station, about 1.3 millisieverts per day during transit. A round trip to Mars, including the surface stay, would expose astronauts to approximately 1.01 sieverts of radiation over the entire mission duration of roughly 1,000 days. To put this in perspective, NASA's current career limit for astronauts is set to keep their risk of exposure-induced death below 3%. A single Mars mission would approach or potentially exceed this lifetime limit. What makes space radiation particularly dangerous isn't just the quantity, it's the quality. We're not talking about the same type of radiation you'd get from an X-ray or even from the fallout of nuclear accidents on Earth. Space radiation consists primarily of two types: galactic cosmic rays and solar particle events. Galactic cosmic rays, or GCRs, are the background hum of the universe, atomic nuclei accelerated to nearly the speed of light by supernova explosions thousands of light years away. They've been traveling through space for millions of years before they slam into your spacecraft. These particles are composed of about 89% protons, 10% helium nuclei, and 1% heavier elements. But it's that 1% of heavy nuclei, things like carbon, oxygen, and iron atoms stripped of all their electrons, that causes the most damage. These heavy ions are what scientists call HZE particles, high charge and high energy. When one of these particles passes through your body, it doesn't just damage the cell it hits. It creates a track of destruction, ionizing everything in its path, shattering DNA strands, and leaving a trail of damaged tissue behind. Unlike the radiation from medical X-rays, which your cells have evolved some ability to repair, HZE particle damage is far more complex and difficult for your biology to fix. The energy spectrum of these particles ranges from tens of millions of electron volts per nucleon all the way up to 50 billion electron volts per nucleon. They're so energetic that they pass right through conventional shielding. In fact, adding more shielding can sometimes make the problem worse through a process called secondary radiation. When a heavy ion hits aluminum, the material most spacecraft are made from, it fragments into lighter particles that spray outward like shrapnel, increasing the radiation dose inside the spacecraft. Then there are solar particle events, or SPEs. These are sudden eruptions from the sun that release enormous amounts of lower energy protons, mostly below 100 million electron volts. While these particles are less penetrating than galactic cosmic rays, they arrive in such huge numbers during solar storms that they can deliver a lethal dose in just hours if you're caught outside with inadequate shielding. On August 7, 1972, right between the Apollo 16 and Apollo 17 missions, one of the most powerful solar flares ever recorded erupted from the sun. If astronauts had been on the moon or in transit during that event, they would have received a potentially fatal radiation dose. We got lucky. The timing saved lives. The challenge with solar particle events is that they're unpredictable. We can't forecast them with enough accuracy to keep astronauts completely safe. During solar maximum, the peak of the sun's 11-year activity cycle, the probability of these events increases, but they can happen at any time. During solar minimum, when SPE probability is lower, the intensity of galactic cosmic rays reaches its peak because the sun's weakened magnetic field allows more cosmic rays to enter the inner solar system. So you're caught in a terrible trade-off. Travel during solar maximum and risk sudden, acute radiation exposure from solar storms, or travel during solar minimum and endure higher continuous exposure from galactic cosmic rays. Neither option is safe with current technology. A comprehensive review published in January 2026 in the European Physical Journal examined the biological effects of this radiation, and the findings are sobering. The research confirmed that radiation exposure doesn't just increase your cancer risk, though that alone is significant, with estimates suggesting a 5 to 10% increase in fatal cancer risk for a Mars mission. The radiation also damages your cardiovascular system, increasing the risk of heart disease and stroke. It affects your central nervous system, potentially causing cognitive impairments, memory problems, and behavioral changes. Recent studies have shown that even moderate doses of HCE particles can cause inflammation in brain tissue, damage to neurons, and disruption of neural networks. Astronauts returning from Mars might face accelerated cognitive decline, something like early-onset dementia. Imagine training for years, traveling for months, working on Mars for a year and a half, then returning to Earth only to find your memory failing, your decision-making impaired, your personality changed. And here's the truly frightening part. These effects might not show up until years after the mission. You can't test for them in advance. You can't know if you'll be one of the unlucky ones whose biology is particularly vulnerable to radiation damage. NASA's current risk models include massive uncertainty ranges because we simply don't have enough data on how the human body responds to long-term exposure to galactic cosmic rays. All our data comes from studying radiation on Earth. Different types, different dose rates, different biological effects. Now you might be thinking, can't we just build better shielding? This is where the physics becomes cruel. To effectively shield against galactic cosmic rays, particularly those heavy HCD particles, you need either enormous mass, think meters of rock or water, or you need active magnetic shielding that creates an artificial magnetosphere around your spacecraft. Passive shielding with mass runs into what's called the tyranny of the rocket equation. Every kilogram of shielding you add requires more fuel to lift it. More fuel adds more mass, which requires even more fuel. The numbers spiral quickly. A recent study on optimal radiation shielding calculated that to reduce the dose below 1 sievert for a Mars mission, You'd need water shielding about 40 to 60 centimeters thick surrounding the entire habitat. For a spacecraft the size of SpaceX's Starship, that's hundreds of tons of additional mass, potentially making the mission impossible with chemical propulsion. Speaking of the challenges of getting back from Mars, I actually created an entire video exploring why returning from the red planet is significantly harder than getting there in the first place. The physics, the fuel requirements, and the timing constraints create a whole separate set of obstacles. If you want to understand the complete picture of Mars travel, check out that video. It's called Why Returning from Mars is Harder Than Getting There. I'll leave a link in the description, and trust me, after you watch it, you'll understand why every Mars mission plan is so obsessively concerned with fuel and launch windows. Active magnetic shielding sounds like science fiction, but it's actually being seriously researched. The concept involves creating a miniature magnetosphere using superconducting magnets that would deflect charged particles around a spacecraft or habitat. A perspective article published in Frontiers in Space Technologies in March 2026 outlined how such systems could work for deep space habitats on the Moon and Mars. The technical challenges are enormous. You need superconducting magnets cooled to near absolute zero, consuming significant power. You need the magnetic field to extend far enough to be effective, potentially hundreds of meters. And you need all of this to be lightweight, reliable, and maintainable for years in the harsh space environment. As of 2026, this technology remains in the early research phase. It's not something we can deploy for a mission launching in the next decade or even two. There's another approach that sounds almost too simple: timing. Research published in Space Weather in 2021 analyzed the optimal launch windows for a Mars mission from a radiation perspective. The study found that launching 4 to 6 months after solar maximum, when solar activity is declining but still high enough to suppress galactic cosmic rays, offers the best window. Combined with trajectory optimization and some passive shielding, this timing could potentially keep the total mission dose below 1 sievert. But here's the problem. Orbital mechanics doesn't care about solar cycles. Mars and Earth align favorably for travel only every 26 months. If your optimal radiation window doesn't coincide with your optimal travel window, you're stuck choosing between a longer, more fuel-intensive journey or higher radiation exposure. Nature doesn't make this easy. The radiation challenge extends beyond just the astronauts themselves. It affects everything. Electronics can be damaged or destroyed by radiation, causing random errors in computer memory, sensor failures, and communication breakdowns. Pharmaceuticals degrade under radiation exposure, potentially losing their effectiveness. Food can be damaged at the molecular level. Even the materials of the spacecraft itself can become brittle and weakened over time. A January 2026 review published in Contemporary Issues in Air and Space Power assessed the challenges of a human mission to Mars and emphasized that radiation protection must be integrated into every single aspect of mission design. From spacecraft architecture to daily operational schedules, from habitat placement to spacesuit design, from food storage to sleep arrangements. You can't just add shielding as an afterthought. The entire mission must be built around minimizing radiation exposure while still accomplishing the exploration objectives. But let's say we somehow solve the radiation problem, either through breakthrough shielding technology, pharmaceutical countermeasures that protect cells from radiation damage, or simply accepting higher risk levels than we currently deem acceptable. We'd still face the second major challenge, the Martian atmosphere itself, or rather, the lack of one. Mars has an atmosphere, but calling it an atmosphere almost feels generous. The average surface pressure is about 600 pascals. That's roughly 0.6% of Earth's sea level pressure. To put this in perspective, the summit of Mount Everest, where climbers struggle to breathe even with supplemental oxygen, has a pressure about 33% of sea level. Mars has 55 times less pressure than the top of Everest. At this pressure, water cannot exist in liquid form on the surface. It either freezes solid or instantly boils away into vapor, skipping the liquid phase entirely in most temperature ranges. This matters enormously because liquid water is essential for life as we know it, for growing food, for industrial processes, for keeping humans alive. Every drop of water on Mars must be kept in pressurized containers or habitats. The atmospheric composition presents another problem. It's approximately 95% carbon dioxide, less than 3% nitrogen, and only 0.13% oxygen. You cannot breathe Martian air, not for a second. If you tried, the carbon dioxide would suffocate you, even as the low pressure caused the gases in your blood to come out of solution, a condition called ebullition. Your blood wouldn't quite boil, despite popular depictions, because your circulatory system is pressurized, but the fluids in your mouth, nose, and lungs would immediately start to vaporize. You'd have maybe 15 seconds of consciousness before passing out. This means that every single moment on Mars requires life support. Every excursion outside requires a spacesuit. Every habitat requires airlocks, pressure vessels, and redundant systems to maintain breathable atmosphere. Unlike Earth, where you can step outside without equipment, Mars demands constant technological mediation between you and the environment. One suit failure, one habitat breach, one airlock malfunction, and people die. The thin atmosphere creates other cascading problems. It provides almost no protection from micrometeorites, tiny space rocks that burn up harmlessly in Earth's thick atmosphere, but slam into Mars at kilometers per second. Your habitat would need to be armored or buried underground to protect against impacts. The thinness also means extreme temperature variations. Without a thick atmosphere to distribute heat, daytime temperatures near the equator might reach a pleasant 20 degrees Celsius, but at night, just hours later, they plunge to minus 70 degrees Celsius or colder. These temperature swings aren't just uncomfortable, they stress materials, cause thermal expansion and contraction that can crack seals, freeze fluids, and cause mechanical failures. Every system must be designed to function across a temperature range of nearly 100 degrees. That's an engineering nightmare. But here's where things get interesting, and this is where recent scientific breakthroughs give us genuine hope. In April 2021, NASA's MOXIE experiment, the Mars Oxygen in situ resource utilization experiment, successfully produced oxygen from the Martian atmosphere. This instrument, no bigger than a car battery, was carried to Mars aboard the Perseverance rover. It works by sucking in Martian air, heating it to about 800 degrees Celsius, and using solid oxide electrolysis to split carbon dioxide molecules into oxygen and carbon monoxide. Over multiple runs, MOXIE demonstrated it could reliably produce breathable oxygen from Martian air. This is genuinely revolutionary. It means colonists wouldn't need to bring all their oxygen from Earth or extract it from water ice. They could make it from the most abundant resource on Mars, the atmosphere itself. The implications ripple outward. Oxygen for breathing, oxygen for rocket fuel, oxygen for industrial processes. Scaling up MOXIE technology would require substantial engineering work. A full-scale system capable of supporting humans and producing rocket propellant would need to be perhaps 100 times larger, require significant power, likely from nuclear reactors, and operate continuously in the harsh Martian environment. But the principle is proven. We know it works. Similarly, water ice exists on Mars in vast quantities, particularly near the poles and in mid-latitude regions just beneath the surface. Radar data from multiple Mars orbiters has mapped these ice deposits. Some locations have ice beginning just centimeters below the dusty soil. This ice can be excavated, melted, and purified to provide water for drinking, growing food, and splitting into hydrogen and oxygen for fuel. The idea of living off the land, called in situ resource utilization or ISRU, trumps the Mars colonization equation. Instead of launching everything from Earth at enormous cost, colonists would arrive with tools and equipment to manufacture what they need from Martian resources. They'd 3D print habitats from Martian soil. They'd grow food in greenhouses filled with Martian dirt enriched with nutrients. They'd manufacture fuel for return vehicles or for exploring further across Mars. An April 2026 study published in Astrobiology outlined a research roadmap for assessing the feasibility of warming Mars using technologies like solid-state greenhouse membranes that could harvest liquid water from subsurface ice, orbiting reflectors to augment sunlight, and engineered aerosols to strengthen Mars's natural greenhouse effect. While these concepts remain speculative and would require decades of research and development, they represent serious scientific thinking about making Mars more habitable over the long term. But even with oxygen production and water extraction solved, we face the biological reality of living in reduced gravity. Mars has about 38% of Earth's gravity. On the surface, you'd weigh a little more than 1/3 of your Earth weight. This sounds liberating. You could jump higher, lift heavier objects, move with ease, and for a short visit, it might be enjoyable. But human biology evolved under one Earth gravity for hundreds of millions of years. Our bodies are fine-tuned to that specific gravitational environment. Take that away or reduce it significantly, and things start to break down. We know this from decades of studying astronauts on the International Space Station, which operates in microgravity, essentially zero gravity. In microgravity, astronauts lose bone density at a rate of about 1 to 2% per month. Their bones, no longer needed to support weight, dissolve calcium into the bloodstream. Muscles atrophy despite rigorous daily exercise. The cardiovascular system weakens because the heart doesn't need to pump as hard to move blood around. Vision changes occur in many astronauts due to fluid shifts that increase pressure inside the skull, a condition called spaceflight-associated neuroocular syndrome, or SANS. Now, Mars isn't microgravity, it's partial gravity. The critical question is 38% enough to prevent these health problems? We honestly don't know. We have extensive data on one gravity, Earth, and extensive data on zero gravity, the ISS and other spacecraft. But we have almost no data on the biological effects of partial gravity at Mars levels. Some scientists hypothesize there might be a threshold below which health problems occur. Maybe 38% is enough to maintain bone and muscle health. Or maybe there's a linear relationship. Less gravity equals proportionally more health problems. Or perhaps it's worse than linear. Maybe even a small reduction in gravity triggers the same cascading failures we see in microgravity. We simply don't have the data yet. The only way to find out would be to build a rotating space station that creates artificial gravity at Mars levels and study people living there for extended periods. NASA and other space agencies have discussed such facilities, but none exist yet. Without this data, we're sending people to Mars blind, not knowing if their bodies will hold up for the 1.5-year surface mission duration. There's another physiological concern that receives less attention, but could be equally serious. the combined effects of radiation and reduced gravity. A study published in NPJ Microgravity in November 2020 highlighted that these two hazards don't just add together, they interact in complex ways. Radiation exposure triggers inflammatory responses in the body. Reduced gravity alters how your immune system functions. Together, they might accelerate aging, increase cancer risk beyond what radiation alone would cause, and compromise your body's ability to heal from injuries. Imagine you're on Mars, 18 months into your surface mission. You slip while working outside and break your arm. Not unlikely given the bulky spacesuit, reduced visibility, and unfamiliar terrain. On Earth, your bones would heal in 6 to 8 weeks. But on Mars, in reduced gravity with chronic radiation exposure, your healing might be significantly slower. Your bone might heal weaker. You might develop complications that wouldn't occur on Earth. And there's no hospital, no emergency room, no specialist you can consult. You have whatever medical equipment and expertise exists within your small crew. This brings us to the psychological challenges, which might ultimately prove just as limiting as the physical ones. A Mars mission represents isolation unlike anything humans have experienced. Yes, we've had people spend a year or more on the International Space Station. Yes, we've had Antarctic research stations where crews winter over in months of darkness. But Mars is different in a fundamental way. On the ISS, Earth fills your window. You orbit the planet every 90 minutes. You can see cities, continents, weather systems. You're still connected to humanity in a visceral way. If something goes catastrophically wrong, you can be back on Earth within hours. Communication with mission control happens in real time. There's no delay. In Antarctica, you're isolated but still on Earth. You breathe Earth air, you experience Earth gravity. You know that when winter ends, a plane will come and bring you home. Mars is nothing like either of these. You're looking at a barren, rust-colored landscape that's never known life. Earth is a star in the sky. You can't see continents or clouds, just a pale blue dot. Communication with home has a time delay ranging from 4 to 24 minutes, depending on planetary positions. When you send a message, you wait up to 48 minutes for a response. You can't have a conversation. You can't call home when you're feeling lonely or scared. You send a message and wait. If something goes wrong, a medical emergency, a life support failure, a psychological crisis, there's no rescue mission coming. The physics of orbital mechanics means that help from Earth would take 6 to 9 months to arrive, and that's only if a spacecraft happens to be ready to launch during a favorable alignment window. More realistically, rescue would take years. You're truly on your own. The psychological term for this is Earth-independent operations, and it represents a quantum leap in the demands placed on crew mental health. A study examining human factors for Mars missions emphasized that crew selection becomes absolutely critical. You need people who can maintain emotional stability under extreme isolation, who can resolve conflicts without outside mediation, who can stay motivated and productive when every day looks the same, when the horizon is always the same rust color, when the sky is always that pale butterscotch pink. You're living in small, confined spaces, probably habitats no larger than a small house shared with 5 to 10 other people. You can't go for a walk outside without donning a spacesuit. You can't open a window for fresh air. You smell the same recycled air, see the same faces, eat the same limited variety of food for months on end. The psychological term is confinement stress, and it's been documented in submarine crews, Arctic expeditions, and long-duration space missions. But it's worse on Mars because you can't leave. On a submarine, you know you'll surface eventually. In Antarctica, you know spring will come. On Mars, you're committed for the full mission duration. likely around 900 days on the surface, waiting for the planets to align for your return journey. That's 2.5 years. And if your return spacecraft has a problem, if something breaks or doesn't work as planned, that timeline extends indefinitely. Psychological screening for Mars crews would need to be far more rigorous than anything we've done before. But here's the problem. We can't perfectly predict who will thrive and who will break under these conditions. Some people who seem psychologically resilient in testing might struggle when faced with the reality. Others might surprise everyone with their adaptability. Human psychology is messy and unpredictable. There's also the question of crew dynamics. Put 6 people together in isolation for 3 years and conflicts will emerge. Personality clashes, disagreements about priorities, resentments over workload distribution, romantic attractions or rejections, all the normal human drama that occurs in any group, but amplified by confinement and stress with no escape valve. Psychological studies of isolated crews have documented the formation of factions, the scapegoating of individuals, the breakdown of communication and cooperation. Mission planners try to mitigate this through careful crew selection, training in conflict resolution, scheduled private communication time with psychologists on Earth, and habitat design that provides some degree of personal space. But ultimately, you're betting that the handful of people you've selected will remain functional and cooperative under extraordinary stress. That's a significant gamble. Then there are the cognitive effects we discussed earlier, the potential for radiation-induced brain damage that could impair judgment, memory, and emotional regulation. Imagine you're the mission commander, and you notice one of your crew members becoming increasingly forgetful, making uncharacteristic mistakes, showing signs of depression or anxiety. Is this just normal psychological stress, or is it radiation damage to their brain? How do you make that determination with limited diagnostic equipment? What do you do about it? Now let's talk about something more mundane but equally critical: food and nutrition. NASA has identified inadequate nutrition as one of the red risks, the highest priority human health risks for Mars missions. This might seem strange at first. Just bring enough food, right? Pack lots of freeze-dried meals, some supplements, maybe bring some treats for morale. Problem solved, except it's not that simple. Food degrades over time, especially under radiation exposure. The vitamins break down, the proteins denature, the taste deteriorates. A study might show that freeze-dried food has a shelf life of 5 to 10 years in Earth storage. But what's the shelf life under constant bombardment by cosmic rays? We don't have complete data on this. Then there's the sheer mass. An average person consumes about 0.6 to 0.8 kilograms of food per day. For a crew of 6 on a 900-day surface mission, that's roughly 3,000 to 4,000 kilograms of food just for the Mars surface stay. Add in the transit periods, about 200 days outbound and 200 days for return, and you're looking at another 1,500 kilograms. You're now talking about shipping over 4.5 metric tons of food, and that's assuming zero waste, perfect preservation, and no emergencies requiring extended stay. This is why every Mars mission plan includes growing food on site, greenhouses filled with plants that convert Martian resources, carbon dioxide from the atmosphere, water from ice, nutrients from enriched soil, into fresh vegetables and possibly even protein from insects or lab-grown meat. The psychological benefits of fresh food and the experience of gardening would also be significant for crew morale. But Martian agriculture faces serious challenges. The soil contains perchlorates, toxic chemicals that would poison plants and humans. The soil would need to be either cleaned or heavily amended with Earth-brought nutrients. The low light levels on Mars, about 43% of Earth's sunlight, would require supplemental artificial lighting, consuming precious power. The need for pressurized greenhouses adds complexity and mass to the mission architecture. Despite these challenges, experiments in analog environments on Earth have shown that it's technically possible to grow a variety of crops in simulated Martian conditions. Potatoes, tomatoes, lettuce, radishes, and various grains have all been successfully cultivated in Mars-like soil simulants. The challenge isn't whether we can grow food on Mars. It's whether we can do it reliably enough, at sufficient scale, with acceptable resource inputs to actually feed a crew for years. There's also the bioregenerative life support question. Plants don't just provide food, they also produce oxygen, consume carbon dioxide, purify water, and contribute to psychological well-being. A fully closed-loop life support system where plants, microbes, and humans exist in a balanced ecosystem would be ideal, minimizing the need for resupply from Earth. But creating such a system that remains stable for years is extraordinarily difficult. Small imbalances can cascade into system failures. The European Space Agency has been studying bioregenerative life support systems for decades through projects like MELISA, Microecological Life Support System Alternative. These experiments have shown that closed-loop systems can work for limited periods, but maintaining long-term stability remains elusive. Oxygen production rates vary with plant health. Water recycling efficiency isn't perfect. Waste products accumulate. Without constant monitoring and intervention, the system drifts out of balance. On Mars, you don't have the option of opening a window or bringing in outside resources if your life support system fails. You're entirely dependent on technology working perfectly every single day for years. The reliability requirements are unlike anything we've engineered before, outside of perhaps nuclear submarines, and submarines can surface if something goes wrong. This brings us to the infrastructure challenge. To support human life on Mars for extended periods, you need far more than just a habitat and a greenhouse. You need power generation, likely nuclear reactors since solar panels are less efficient on Mars and dust storms can block sunlight for weeks. You need water extraction and purification systems. You need oxygen production from MOXIE-type devices. You need carbon dioxide removal from habitats since it builds up quickly in enclosed spaces. You need waste management systems that can recycle human waste into useful products. You need workshops with tools and spare parts to repair equipment when it breaks, and things will break constantly in the harsh Martian environment. You need communication systems with large antennas to maintain contact with Earth. You need rovers and equipment for exploring and working outside. You need spacesuits, multiple suits per person with spare parts because suits wear out. The list goes on. Airlocks, radiation shelters, medical facilities, laboratories for scientific research, storage for supplies, thermal control systems to manage temperature extremes, dust mitigation systems because Martian dust gets into everything and is highly abrasive. Each system needs redundancy because there's no running to the hardware store if something fails. Estimating the total mass of infrastructure needed for a sustainable Mars base is sobering. Some studies suggest that even a minimally viable base supporting 6 to 10 people would require landing hundreds of metric tons of equipment and supplies on Mars before the first crew arrives. SpaceX's Starship is designed to land about 100 metric tons on Mars per flight. You're talking about multiple cargo missions, perhaps 5 to 10 flights, just to set up the basic infrastructure, all successfully automated and deployed robotically before humans arrive. And every one of those cargo flights needs to launch during the 26-month Earth-Mars transfer windows when the planets are properly aligned. Miss a window, and you wait over 2 years for the next opportunity. If a critical piece of equipment fails to land successfully or doesn't deploy properly, the entire mission timeline shifts by years. This is why SpaceX's February 2026 announcement about delaying Mars plans was significant. The company has been working on demonstrating orbital refueling, transferring propellant between starships in Earth orbit. This capability is essential because a starship heading to Mars needs to be filled with roughly 1,200 metric tons of cryogenic propellant, requiring multiple tanker flights to fill a single Mars-bound ship. As of mid-2026, this orbital refueling hasn't been successfully demonstrated yet. Without proven orbital refueling, you can't send heavy payloads to Mars efficiently. Without landing heavy payloads, you can't build the infrastructure needed to support humans. The entire architecture depends on getting this fundamental technology working reliably. And that's just one example. There are dozens of other technologies that need to advance from concept to proven hardware before a crewed Mars mission becomes feasible. China has announced its own Mars ambitions, with plans for sample return missions in the late 2020s and potential crewed missions in the 2040s. Their approach appears more incremental, building capabilities step by step through lunar missions first, developing and testing technologies before committing to Mars. This methodical approach might ultimately prove more successful than aggressive timelines that repeatedly slip when confronted with technical realities. There's also the question of what happens when things go wrong, because they inevitably will. Spacecraft are complex machines with thousands of components, any one of which can fail. Habitats are pressure vessels subject to stress and fatigue. Suits develop leaks. Equipment wears out. In the history of space exploration, we've had countless close calls and several tragedies. The Apollo 13 mission nearly ended in disaster when an oxygen tank exploded. The Space Shuttle Challenger was destroyed during launch. The Space Shuttle Columbia broke apart during re-entry. The ISS has had debris strikes, ammonia leaks, and computer failures. On the ISS, when something goes seriously wrong, the crew can evacuate in Soyuz capsules and be back on Earth within hours. On Mars, there's no evacuation option. You deal with the emergency using whatever resources and ingenuity you have available, or you die. The crew must be capable of diagnosing and repairing virtually any failure with limited tools and parts. They become mechanics, plumbers, electricians, computer technicians, chemists, and doctors all at once. This requirement for extreme self-sufficiency drives crew selection and training to unprecedented levels. Astronauts already undergo years of training for space missions, but Mars crews would need even more comprehensive preparation. They'd need to understand their spacecraft and habitat systems at the component level. They'd need medical training sufficient to perform surgery if necessary. They'd need geological training to identify resources and hazards on Mars. They'd need botanical and agricultural knowledge to maintain food systems. They'd need psychological training to support each other through crises. The romantic notion of Mars explorers as brave pioneers pushing humanity's boundaries is true, but the reality is they'd also be living maintenance manuals, spending much of their time on routine repairs and system checks. The adventure would often feel like being a superintendent in an apartment building, constantly fixing things to keep the plumbing and heating working, except the building is millions of kilometers from help, and the stakes are life and death. Let's discuss the communications delay more deeply because it affects decision-making in ways that aren't immediately obvious. On Earth, when NASA Mission Control sees a problem developing, They can immediately talk to astronauts and work through solutions in real time. On Mars, by the time Mission Control sees a problem developing, sends instructions and receives confirmation, between 8 and 48 minutes have passed depending on planetary positions. If something is actively going wrong, a pressure leak, a fire, a medical emergency, 40 minutes is far too long to wait for advice. The crew must assess the situation and act immediately based on their own judgment. Mission control becomes more of a planning and support function rather than active operational control. This represents a fundamental shift in how space missions operate. It also means that crew training must emphasize autonomous decision-making and leadership in every member. Traditional mission structures with clear hierarchies and deference to ground control won't work. The Mars crew becomes their own mission control, making life or death decisions with imperfect information under time pressure. The psychological weight of this responsibility is immense. There's another aspect of the communications delay that touches on something deeply human: connection to home. Imagine calling a loved one to share good news or seek comfort during a difficult moment, and instead of hearing their voice, you wait 20 minutes, then receive a recorded response, then wait another 20 minutes for them to hear your reply. It's not a conversation, it's an exchange of monologues separated by agonizing silence. The emotional intimacy that comes from real-time interaction is impossible. Astronauts on the ISS frequently report that regular communication with family is crucial for psychological well-being. They can video call home, see their children, have conversations. Mars crews would lose this. They'd receive news from Earth that's already 20 minutes old. They'd watch events unfold: births, deaths, weddings, crises, with a temporal disconnect that would make them feel like observers of their own lives rather than participants. Research into the psychological effects of communication delays suggests this could be one of the most challenging aspects of Mars missions. Humans are intensely social creatures. We need connection, particularly during stress. The inability to have real-time contact with anyone outside your small crew could lead to feelings of isolation and disconnection that go beyond physical distance. You're not just far from Earth. You're temporally separated, existing in a different time stream where everything you learn about home is already in the past. Now let's turn to something that receives less public attention but keeps mission planners awake at night: Martian dust. This might sound trivial compared to radiation and life support challenges, but dust is a pervasive, insidious problem that affects every single system. Martian dust particles are extraordinarily fine, averaging about 3 micrometers in diameter, much finer than talcum powder. The dust is also highly electrostatic due to the dry environment and solar ultraviolet radiation, causing it to cling to everything. During the global dust storms that sometimes envelope Mars for months, this dust fills the air, reduces visibility to meters, blocks sunlight, infiltrates seals, and coats every surface. The Mars rover's Spirit and Opportunity were designed for 90-day missions but operated for years. Spirit for 6 years and Opportunity for nearly 15 years. Eventually, both succumbed not to mechanical failure, but to dust. Spirit's solar panels became so coated with dust that it couldn't generate enough power and went silent. Opportunity survived longer, partly due to occasional cleaning events when wind would blow dust off its panels, but ultimately a massive dust storm in 2018 coated its panels so thoroughly that it couldn't recharge and the mission ended. For human missions, dust creates multiple hazards. It's abrasive, wearing down mechanical seals, scratching visors and windows, degrading solar panels. It's toxic. Martian regolith contains perchlorates and other chemicals you definitely don't want in your lungs. It's clingy. Astronauts coming inside from surface excursions would bring dust with them despite best efforts, contaminating habitats. Over time, this dust would accumulate in air filters, on surfaces, in equipment. The Apollo astronauts experienced similar problems with lunar dust, which is even more abrasive due to its sharp, unweathered edges. They reported that despite attempts to brush it off, dust got everywhere, in their suits in the spacecraft, in their eyes and lungs. Some astronauts experienced respiratory irritation from inhaling lunar dust particles, and that was for missions lasting days. On Mars, you're dealing with years of continuous exposure. Airlocks become critical dust mitigation choke points. Crews would need to spend time in airlocks carefully cleaning suits and equipment before entering habitats. But no cleaning is perfect, and over months and years, dust accumulation inside habitats becomes inevitable. This dust could trigger allergies, respiratory problems, and equipment malfunctions. It's a slow degradation of the living environment that compounds over time. Dust storms also directly threaten mission operations. If solar panels are your primary power source, a global dust storm could reduce power generation to near zero for weeks or months. This is why most Mars mission architectures rely on nuclear power systems instead. Small reactors that work regardless of atmospheric conditions. But nuclear systems bring their own challenges. They're expensive, politically controversial, require extensive safety engineering, and have limited lifespans. The Kilopower project, developed by NASA and the Department of Energy, demonstrated a small nuclear reactor designed specifically for space applications. A unit generating about 10 kilowatts could provide power for a small Mars outpost, but you'd likely need multiple reactors for redundancy and sufficient power. Each reactor represents a complex, sensitive piece of equipment that must function flawlessly for years in the Martian environment. If they fail, you lose power, and without power, everything else fails. Life support, heating, water recycling, oxygen generation. Let's discuss entry, descent, and landing on Mars, often called the 7 minutes of terror in reference to the Curiosity rover landing. Mars's thin atmosphere creates a dilemma for landing spacecraft. The atmosphere is thick enough to cause heating and require heat shields, but too thin to rely solely on parachutes for landing heavy payloads. Every successful Mars lander has used a combination of heat shields for initial deceleration, parachutes for mid-phase descent, and then rockets for the final landing. The largest payload successfully landed on Mars is the Curiosity rover at roughly 900 kilograms. The Perseverance rover, landed in February 2021, had a similar mass. Landing something as large as SpaceX's Starship, 100 metric tons or more, represents an entirely different scale of challenge. Starship's proposed landing approach uses supersonic retropropulsion, firing engines against the direction of travel while still moving at supersonic speeds through the atmosphere. This technique has been demonstrated in Earth's atmosphere with Falcon 9 boosters, but never in Mars's thin atmosphere at the scale and speed required. The engineering challenges are formidable. Controlling a massive top-heavy spacecraft during descent, managing propellant consumption to land with sufficient fuel reserves, dealing with engine plume interactions with the surface that could kick up debris, and ensuring landing leg stability on unknown terrain. A single Starship landing successfully would be a technological achievement. But remember, a sustainable Mars base requires multiple cargo flights delivering hundreds of tons of equipment. Every single one needs to land successfully in the right location. Mission planners would likely land cargo ships first, verify successful deployment, then commit to sending crew. but each landing is a high-risk event. Statistically, Mars missions have about a 50% success rate historically, though that's improved in recent years. Still, you're rolling the dice with every landing. The landing site selection becomes crucial. You need a location that balances multiple competing requirements: relatively flat terrain for safe landing, proximity to water-ice deposits for resource extraction, interesting geology for scientific research, good solar exposure for power generation if using solar panels, low elevation for thicker atmosphere during landing, and moderate latitude to avoid extreme cold. NASA has identified several candidate regions for human missions, including locations in Deuteronomus Mensae, Phlegra Montes, and Arcadia Planitia, all in the mid-northern latitudes where subsurface ice is abundant, but temperatures aren't as extreme as the polar region. But selecting the final site requires reconnaissance, high-resolution orbital imagery, possibly scouting missions with robotic landers to test the soil and identify hazards. This all takes time and multiple missions before humans arrive. There's also the question of what happens if the landing doesn't go perfectly. Let's say a starship lands successfully but tips slightly on uneven ground. Is it still usable? Can the crew access it safely? Can cargo be unloaded? Or is it a total loss? With such high-value payloads and limited mission opportunities, a single landing failure could cascade into mission delays of years or even cancellation. Then there's the return journey to consider. Unlike Apollo missions to the Moon, where the return vehicle orbited waiting for astronauts, Mars missions face a different challenge. The spacecraft that takes you to Mars becomes your home in Mars orbit or on the surface. To return, you need propellant, lots of it. Roughly 1,000 to 1,200 metric tons for a Starship-class vehicle. Bringing that propellant from Earth is impractical due to mass constraints. This is why SpaceX's architecture depends on in-situ propellant production, manufacturing methane and oxygen fuel from Martian resources. The Sabatier process can create methane from carbon dioxide and hydrogen, while electrolysis splits water into hydrogen and oxygen. In theory, you land with hydrogen feedstock and power systems, then spend 18 months manufacturing the propellant for your return trip. But this assumes everything works perfectly. The equipment must function reliably for months of continuous operation in the Martian environment. You need sufficient water ice accessible nearby and the equipment to extract and purify it. You need enough power to run energy-intensive chemical processes. If propellant production falls behind schedule or equipment fails, your return window closes and you're stuck on Mars for another 26 months until the next transfer window opens. Imagine being on Mars, watching your propellant production system struggle to meet targets. Every day you're doing the math. If we continue at this rate, will we have enough fuel to get home? Do we ration power from other systems to prioritize fuel production? Do we extend our stay and wait for the next window? What if the system fails completely? Are we stranded indefinitely? This uncertainty creates a psychological burden beyond the physical challenges. You're entirely dependent on technology working in ways it's never been tested at this scale. In an environment where troubleshooting is difficult and replacement parts are impossible to obtain. The knowledge that your ticket home is being manufactured molecule by molecule over months, with no backup plan if it fails, would weigh on anyone's mind. Let's talk about the financial dimension, because ultimately, Mars colonization isn't just a technical challenge, it's an economic one. Space missions are extraordinarily expensive. The Apollo program cost approximately $150 billion in today's currency. The International Space Station has cost over $150 billion for construction and operations. These projects had the full backing of governments and were justified by Cold War competition or international cooperation goals. A Mars mission would cost significantly more than Apollo. Some estimates suggest between $500 billion and $1 trillion for a complete program including development, testing, cargo missions, crew missions, and establishing a permanent base. That's an enormous sum that's difficult to justify on scientific grounds alone, especially when robotic missions can accomplish much of the science for a tiny fraction of the cost. SpaceX claims they can reduce costs dramatically through reusability and economies of scale, potentially bringing mission costs down to the tens of billions rather than hundreds of billions. But even the optimistic scenarios require enormous capital investment, far more than any private company has available. SpaceX would need sustained funding from governments, international partnership, or some economic return model that makes Mars commercially viable. This brings us to the question, what's the economic justification for Mars colonization? The Moon has potential economic value, helium-3 for fusion reactors, if we ever develop practical fusion, rare earth elements, a platform for space-based solar power or manufacturing. But Mars? The resources available on Mars, water, minerals, even exotic materials, aren't valuable enough to justify the cost of extracting and returning them to Earth when similar materials are available here or on the Moon with far lower transportation costs. Some advocates propose that Mars colonization isn't about economic return to Earth, but about creating a self-sustaining second location for human civilization, a backup drive for humanity. If Earth becomes uninhabitable due to nuclear war, asteroid impact, runaway climate change, or other catastrophes, having humans established on Mars preserves the species and our civilization. This is essentially an insurance policy argument. The philosophical appeal is obvious, not putting all our eggs in one planetary basket. But the practical economics are challenging. Insurance only makes sense if the premium is affordable relative to the risk being mitigated. Is spending $1 trillion on Mars colonization the most effective way to ensure human survival? Could that same money prevent existential risks on Earth? Asteroid detection and deflection, pandemic preparedness, climate change mitigation, nuclear weapons reduction. This isn't to say Mars colonization has no value. The inspiration it provides, the technological advancement it drives, the expansion of human knowledge and experience are all legitimate benefits. But inspiration doesn't pay for rockets, and technology development can happen through less expensive means. For Mars colonization to move from aspiration to reality, someone has to write enormous checks over decades, accepting that there won't be financial returns in any conventional sense. Currently, government space budgets are measured in billions per year, not the trillions needed for Mars. NASA's budget is roughly $25 billion annually, substantial but spread across many programs including Earth science, ISS operations, lunar programs, robotic missions, and technology development. Dedicating the resources needed for Mars would require either massive budget increases or eliminating almost everything else NASA does. Neither seems politically viable given other spending priorities like healthcare, education, infrastructure, and defense. China's space program is growing, but they're currently focused on lunar exploration and building their space station. Their Mars ambitions extend into the 2040s, suggesting a timeline measured in decades, not years. International collaboration could distribute costs, but coordinating such programs across different governments with different priorities and political systems has proven challenging even for relatively modest projects like the ISS. This is why, despite decades of aspirational timelines, humans remain stubbornly on Earth, and in low Earth orbit. The technology challenges, while significant, are arguably solvable given sufficient resources and time. The fundamental barrier is economic and political will, sustaining the enormous investment required over the 20 to 30 years needed to develop, test, and deploy all the systems for a Mars mission. Private companies like SpaceX change this equation somewhat. They can operate with longer time horizons than government programs subject to political cycles. They can take risks that government agencies, accountable to taxpayers and cautious after past tragedies, are reluctant to accept. But they still need funding, and SpaceX's current business model, launching satellites and cargo for paying customers, doesn't generate anything close to the revenue needed for Mars colonization. Elon Musk has suggested that a fleet of starships, manufactured at scale and flying frequently, could reduce the cost per person to Mars to perhaps $100,000 to $500,000, comparable to the cost of a house. At those prices, potentially thousands of people might choose to emigrate to Mars as settlers, creating a self-funding colonization model. But this assumes Starship achieves full reusability, flies frequently without major failures, and that people are willing to invest their life savings to move to a harsh, dangerous environment with no possibility of return for years and uncertain prospects for survival. The comparison to historical colonization efforts is instructive but imperfect. European colonization of the Americas was driven by economic opportunities, gold, furs, tobacco, sugar that could generate profit. Settlers faced hardship but arrived to find breathable air, drinkable water, edible plants, and buildable materials. Mars offers none of these advantages. It's less like sailing to the New World and more like trying to establish a permanent settlement in Antarctica, except Antarctica is vastly more hospitable than Mars and can be reached in days rather than months. Or historical Antarctic exploration provides perhaps the better analogy. Multiple expeditions in the early 20th century pushed to reach the South Pole and explore the continent. Many ended in tragedy. Scott's expedition perished on the return from the pole. Shackleton's endurance was crushed by ice. These expeditions were funded by national pride and scientific curiosity, not economic returns. Today, Antarctica hosts research stations, but no permanent colonization. People rotate through on temporary assignments. No one is born there. No self-sustaining economy exists. Mars might follow a similar trajectory. Research outposts visited by rotating crews, scientific missions advancing our understanding, perhaps even small-scale resource extraction to support those operations. But the vision of cities on Mars, of terraforming the planet to be Earth-like, of millions of people living there, these ideas start to look less like near-term possibilities and more like science fiction when confronted with the realities of biology, physics, and economics. Terraforming Mars specifically deserves discussion because it's often presented as the ultimate goal of Mars colonization. The idea is to modify Mars's environment to make it more Earth-like, thicken the atmosphere, warm the planet, possibly create liquid water oceans, maybe even introduce oxygen to make the air breathable. If successful, Mars would transform from a hostile environment requiring constant life support into a genuine second home for humanity. The concept has been explored scientifically for decades. Carl Sagan discussed planetary engineering in the 1970s. NASA scientists published studies in the 1990s examining potential approaches. More recently, researchers have conducted detailed analyses of Mars's resources and what would be required for terraforming. The typical proposal involves releasing Mars's carbon dioxide reserves, currently frozen at the poles and in the regolith, to thicken the atmosphere and create a greenhouse effect that warms the planet. This could be done by setting up factories producing powerful greenhouse gases, by using orbital mirrors to focus sunlight on the poles and sublimate the ice, by deliberately impacting dark asteroids to reduce Mars's albedo, or through other large-scale engineering interventions. In theory, if you could warm Mars sufficiently, frozen carbon dioxide and water would sublimate and melt, thickening the atmosphere and creating a runaway warming effect. Eventually, you might achieve stable liquid water on the surface and atmospheric pressures high enough that humans would only need oxygen masks rather than full pressure suits. But recent research has thrown cold water on these optimistic scenarios. A comprehensive study published in Nature Astronomy in July 2018 examined Mars's carbon dioxide inventory in detail. The researchers concluded that even if you released every accessible carbon dioxide molecule on Mars, from the polar caps, from absorbed gas in the regolith, from carbonate minerals, you wouldn't generate enough atmosphere to significantly warm the planet or achieve pressures high enough for liquid water stability. Mars simply doesn't have enough volatile materials remaining to terraform through atmospheric thickening alone. Most of Mars's original atmosphere was lost to space billions of years ago, stripped away by solar wind after the planet's magnetic field shut down. That carbon is gone, ejected into space or locked in minerals deep underground where it's inaccessible with any foreseeable technology. This finding doesn't completely eliminate terraforming as a theoretical possibility, but it makes it vastly more difficult. You'd need to import massive amounts of volatiles from elsewhere, perhaps by redirecting comets or asteroids rich in water and carbon dioxide to impact Mars. But we're talking about thousands or tens of thousands of impacts over centuries, each requiring precise orbital manipulation of objects weighing billions of tons. The energy requirements are astronomical, and the precision needed to avoid destroying any existing infrastructure makes it a project of staggering complexity. Even if you could somehow thicken Mars's atmosphere, you face other fundamental problems. Mars lacks a magnetic field, so the thickened atmosphere would slowly leak away to space, just as the original atmosphere did. You'd need to continuously replenish it or find some way to generate a protective magnetic field, perhaps through enormous superconducting rings at Mars's poles, creating an artificial magnetosphere. Such megastructure engineering projects move firmly into the realm of civilizations far more advanced than ours. There's also the time scale. Even optimistic terraforming scenarios involve centuries to millennia of sustained effort. You'd need multiple generations of humans dedicating enormous resources to a project whose benefits wouldn't be realized in their lifetimes. This requires a level of long-term commitment that's virtually unprecedented in human history. Most of our projects think in terms of years or decades, not centuries. So the realistic near to medium-term future for Mars is likely enclosed habitats, underground or heavily shielded facilities, constant dependence on life support systems, and a population measured in dozens or perhaps hundreds rather than millions. Not the sweeping cities under vast domes of science fiction, but something closer to Antarctic research stations, functional, austere, focused on specific objectives, and inhabited by people who plan to eventually return to Earth. This mean Mars colonization is impossible or not worth pursuing? Not necessarily. It means we should be realistic about timelines, costs, and what's actually achievable. The first human missions to Mars, when they happen, will be extraordinary achievements. Proof that humans can operate beyond the Earth-Moon system. Demonstrations of technologies that might enable further exploration, expansions of scientific knowledge. Those first missions might establish permanent outposts that persist over decades, gradually growing as technology improves and costs decrease. Over generations, perhaps centuries, those outposts might evolve into something larger, settlements with their own culture, economies based on supporting further space exploration, perhaps specialized industries taking advantage of Mars's unique environment, like low-gravity manufacturing or astronomical observations. But this is a vision measured in timelines far longer than most Mars colonization advocates acknowledge. Elon Musk's goal of 1 million people on Mars by the 2050s is, in this context, somewhere between wildly optimistic and physically impossible given current technology and resources. Even getting 1,000 people to Mars by 2100 would be a remarkable achievement requiring sustained commitment across multiple generations. Let's talk about what early Mars bases would actually look like in practice. Forget the artistic renderings of gleaming habitats with large windows overlooking rust-colored vistas. Real Mars bases would likely be austere, cramped and largely underground, or covered with regolith for radiation shielding. The habitat modules would probably be cylindrical pressure vessels, partially buried and covered with several meters of Martian soil. This shielding provides both radiation protection and thermal insulation. Interior spaces would be maximally functional, sleeping quarters barely larger than a closet, communal areas serving multiple purposes, every cubic meter utilized because bringing habitat volume from Earth is expensive. Wendon, if they exist at all, would be small and heavily shielded, perhaps thick layers of water in the walls serving as both radiation shielding and windows. The view outside would show a barren, rocky landscape, reddish-brown soil, distant rock formations and a salmon-colored sky. No trees, no grass, no animals, no flowing water, just sterile geology under a thin, poisonous atmosphere. The daily routine would involve constant system maintenance, checking air recyclers, cleaning water filtration systems, monitoring power generation, inspecting seals and pressure integrity, tending plants in the greenhouse, troubleshooting equipment failures. The work would be repetitive, technical, and critical. One mistake or overlooked problem could cascade into a life-threatening situation. Extravehicular activities, going outside, would be major undertakings requiring hours of preparation. Suits would need checking, life support systems verified, batteries charged, tools gathered. The actual time outside might be limited to a few hours before returning for the lengthy decontamination process to remove toxic dust. Those outside excursions would be scientifically valuable, but physically exhausting and mentally stressful. Meals would come from stored provisions for the first years, supplemented gradually by greenhouse produce as those systems mature. Don't expect gourmet dining. Think nutritionally optimized but monotonous food, reconstituted freeze-dried meals, the same limited variety of vegetables that grow efficiently in controlled environments. Spices and condiments would be precious luxuries to break the monotony. Entertainment and recreation would be limited to what you can bring digitally or create locally. There's no going to movies, restaurants, concerts, or sporting events. No hiking in forests or swimming in oceans. Your world is confined to a few hundred square meters of pressurized space and whatever virtual experiences you can access through recorded media. The communications delay makes real-time internet interactions impossible. You can browse archived web content but can't participate in live conversations or multiplayer games with people on Earth. Exercise would be mandatory to counteract the effects of one-third gravity, but confined to treadmills, resistance equipment, and whatever limited space is available. The variety of physical activities possible on Earth, from swimming to rock climbing to team sports, would be mostly impossible.